Hello. Please. 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 Oh. Choose one or two. I want to thank everyone who sent me questions. I've got questions and I have to be fast enough to cover all questions sent to me. So and this question is directly related to one of the questions I received from some of you. So do you agree that if the net force is 0, the object is definitely at rest? I've got some toys. So, okay, a quarter still has a confusion between velocity and acceleration, how these variables are related. So the correct answer is no, because if the net force is 0, that only means what? Acceleration is also 0. That's for sure. That's the Newton's second law tells us. However, if the acceleration is 0, it doesn't mean the velocity also has to be 0. The acceleration is 0 means velocity doesn't change. That's it. What? That's it. So this is a question I got from someone. How an object can have a constant velocity but still have net force equals 0? Well, how? Because of the Newton's second law. The Newton's second law does not govern velocity. It governs acceleration. So when we say motion, that word motion means displacement, means velocity. That's what it means. When we say force, that means acceleration. All right. So this versus this. It stops because of friction. We have to use our imagination. We have to imagine what would happen with no friction at all, almost frictionless, an infinitely long bench. In that case, it would be moving forever, keeping velocity constant. We don't have to apply a force to keep an object moving. We need to apply a force to make it move. Like it's at rest, net force is 0. During my touching it, stop. During my finger touching it, the net force wasn't 0, of course. I'm speeding it up. But if it doesn't touch anymore, that's it. Imagining there is no friction, It will be traveling with constant velocity forever. So that's actually a statement which we call Newton's first law. We don't have to apply a force to keep an object moving. So first, second, third is going to be fourth. Newton was a genius. Now, this simple experiment gives us, well, a picture we always can use to support this relationship between force, mass, acceleration. It's speeding up, actually. You know what? Just for the sake of having it in the movie also. Stops. Never stops. This fan provides a certain amount of force. So that's why it's moving faster and faster. Again, neglecting friction, it will be moving faster and faster and faster forever. In real life, eventually, the air friction balances out the force, and it reaching terminal velocity, and after that, keeps traveling with constant velocity. But in, well, ideal world, again, it will be speeding up forever. Now, use your imagination. Imagine you have a second fan identical to this. You double the force. If you double the force, you use an ultramotion sensor, you measure acceleration. Acceleration also doubled. Now imagine that you add in a mass. If you double the mass, again, you take a motion sensor, you measure acceleration. Acceleration goes in half. That's it. That's what the Newton's second law tells us. Plus, in addition, Newton's law tells us that if many forces acting first, we gotta add them up together as vectors to get the net force, and the net force will be proportional to mass and acceleration. Another illustration. Almost frictionless motion, and we give it a kick. See? The kick changed the trajectory. Before the kick, it was traveling with constant velocity. During the kick, it changed its velocity. The force means acceleration is not zero. Acceleration is not zero, velocity changes. But after the kick, it again keeps traveling with constant velocity. Because after the kick, the net force is zero again. What's going to happen if instead of one kick, we're going to keep kicking it? Let's see. Et cetera, et cetera, et cetera. So it wasn't traveling straight anymore. Every kick gave an additional change in the velocity. So that's what we call constant force acting on it, right? Many, many kicks acting together basically provide a constant force. That's it. So in that situation, instead of traveling with new constant velocity, well, this is the same situation. A quick burst means almost instantaneous change in the velocity, and that's it. But if the engine actually keeps providing constant force, in that case, every additional pulse changes the velocity, and in that case, the trajectory is not straight line anymore. It's actually a parabola. Imagine that picture just flipped over. Do you have in mind any constant force which is acting on any object which is close to the Earth? What kind of a constant force acting on everything close to the Earth? gravity. So this is exactly the same situation. Constant force constantly changes its velocity. So the trajectory now will be, after this point, a parabola. And that's another question I received in my email. So this is the source. Any problem on the exam resemble one of these problems, one of the problems you've seen before. Where and when? Here in this room, on the screen, or in a discussion section when you read the assignment, or in a lab when you read the lab manual, or I don't know where you do your homework, but you should do it somewhere. So when you do the homework, you see the problems, which will be similar to the problems in the exam. If you want to look at the, well, something similar to the exam per se, you can print out randomly 8 problems, 1 problem per page, staple, attach the equation sheet from the blackboard. That's going to be the exam. Question 10 of homework 5. Well, first of all, there is no homework 5. There is homework 1, part 5. So that was my assumption that the problem talked about this. Otherwise, I might have a wrong impression. So this is a situation when an object sliding down a ramp or something else. So what I'm solving is this. Homework 1, part 5. And the homework 2 now is also available for people who want to start early. And the initial velocity is 0. And force of normal force, force of gravity, and the force of kinetic friction, because it slides, it's kinetic, is acting. This is the free body diagram. And we need to relate time, mass, distance traveled, and acceleration. These variables are supposed to be related. And the coefficient of kinetic friction, and frictional force itself. And as we know, they have to be also related to the normal force, force of gravity, and the abstract force, which we call the net force. So this is the set of variables. Let's add a final velocity. This is the set of variables we have to relate to each other. And we know that to do that, we have to use 2 sets of equations. One set of equations related to motion with constant acceleration. Second set of equations related to, well, Newton's second law and forces, everything about forces. So the first set of equations tells us that for a motion with constant acceleration, the distance traveled, well, in this situation, is equal to the displacement. And for the displacement, we can apply the motion equation, initial velocity times time, plus acceleration times time squared divided by 2. This is 0 because of that. We know distance. We know time. Why? Because we can read. So that gives us acceleration. And of course, now we can immediately calculate final velocity. The initial velocity plus acceleration times time. So this part has nothing to do to forces at all. Nothing. But now, since we know the acceleration, we can move on to the next phase of the solution, and we can calculate everything, basically, you know. So x and y relative to the x axis. That's g. M times a supposed to be equal to mg sine theta minus friction. And in this equation, we know mass, we know acceleration, mass g angle, so that gives us friction. That's the logic. Now, what do we know about friction? Well, friction is related to, where is it? Is related to the normal force. Some people like writing that force of friction is equal to coefficient times mg. That's just wrong. Sometimes it does work, but sometimes, not always. So this is the equation we have to write. And then, depending on the situation, we should calculate the normal force correctly. And in this situation, the normal force is not equal to mg. In this situation, the normal force is equal to what? mg times cosine of theta. And because we know the frictional force and because we know the normal force, that answers the question about the coefficient. How to calculate contact forces? Well, there are no contact forces, strictly speaking. There's only one contact force, this one. But it has two components, which we don't call contact forces. We call them by different names. The parallel component of the contact force has a name frictional force, and the perpendicular component has a name normal force. So, to calculate the normal force, we use the Newton's second law. We choose the direction like that, and we write the Newton's second law relative to this axis. F net y will be equal to m times the y component of the acceleration. For the frictional force, we have to use the x component of the same law. F net x should be equal to m times the x component of the acceleration, assuming, of course, the natural choice for x and y axis. If you mean you want to calculate the contact force per se, you have to use the Pythagorean theorem. The contact force, the normal force, and the frictional force always form a right-angled triangle. So if you want to calculate the magnitude of the contact force, you have to apply the Pythagorean theorem. So just probably I was a little too fast, so let's just do it one more time, a little bit slower. In addition to the applied force, we should introduce three other forces acting on this piece of ice: gravity, normal, friction. What kind of a friction? Of course, that's kinetic friction because it's sliding. Velocity is not zero. What about acceleration? That depends. Bless you. The acceleration can be equal to zero, case A, which means the velocity is constant, which means net force equals zero. This happens only when applied force has the specific magnitude, nor more nor less a certain value. That's a case one. What is the magnitude of the applied force? Case two, the magnitude of the, that's a critical value. The magnitude of the applied force is above that critical value. In that case, acceleration is not zero anymore. Velocity is not constant anymore. Well, let's start from a case two. In the latter case, case two, if acceleration is not zero, this is what we should write. Again, x, y. The applied force times cosine of 25 degrees, that represents the x component of the applied force, minus the force of kinetic friction. That's the Newton's second law written relative to the x component. Relative to the y component, the same law should write zero because the acceleration doesn't point up or down. So the applied force has a vertical component, which is equal to the magnitude of the applied force times the sine of 25 degrees. Now, the normal force also points up, and the force of gravity points down. And the third equation we can write is the relationship between the force of kinetic friction and the normal force. The force of kinetic friction comes in here, the normal force comes in here. So what you could have done is replace normal force, equation 1, equation 2, equation 3. You use equation 3 to solve it for normal force and plug it in equation 2. Then you can use the modified equation 2 to solve it for the frictional force and plug it in equation 1, for example. In the end, you have only one equation, and that equation will give you the answer for the acceleration. Here we are assuming that we know the magnitude of the applied force. The applied force is given. We know it. We know it's above the critical value. What is the critical value? Well, for the critical value, we use exactly the same set equations. We just set the acceleration to 0. So F times cosine of 25 minus kinetic friction equals 0. F times sine of 25, and that's a critical value, plus normal force minus mg equals 0. And the same equation still stays because it's still moving. So friction is kinetic. In this situation, so we can apply the same kind of reasoning. First, we can do this, and then we can, well, actually, do it like that. You end up with one equation which has only one unknown left, kinetic friction, the force itself, and you solve it for that force. That's math. So this is what is happening. The picture is very important, and well, normally we do something like that. Now, what do we know? Well, this is the special position, and that position should be equal to negative 6,000 meters. Like 6 3/4, I don't know, 6,000. Why it's negative? Well, if I choose my origin at the initial location and I point x direction to the right and I travel 6,000 meters to the left, the position is negative, the x coordinate is negative. And then you travel 30 meters to the right. So x final is equal to, well, negative 6,000 plus 300. And of course, there is time you spent walking to the left. There is time you spent walking to the right. And this arrow represents your average velocity for the total trip. This arrow represents your velocity on your way to the left. And this arrow, sorry. I meant displacement. So displacement. This arrow represents your total displacement. This arrow represents your displacement delta x on your way down. The left, this arrow represents your displacement. But displacement over time is velocity. So we can write immediately three equations. Delta x1 over t1 equals v1, which in numbers, delta x1, negative 600 minus 0 divided by t1 equals negative 34. That's the speed. Yeah. You walked west, so to the left. v1 points to the left, has a negative component. You can solve this equation. That gives you t1. Second equation, delta x2 divided by t2 equals v2. So x final minus x initial for this particular part of the trip divided by t2 equals v2. This equation has two unknowns, unsolvable. But we can write the third equation for the whole trip. Delta x divided by total time should be equal to something that your final average velocity is 2 point. That should be west, or that should be a different number. Because if you ended up here, your final velocity should be like that. So V average total. In numbers, your final position is this. Your initial position for the whole trip is this. Your total time is t1 plus t2, and that should be equal to negative 2.8. So now t1 is a known number, and what you have here, two equations. You can solve, well, first you can calculate the t2 from the bottom equation, and then you can use it to calculate v2. All right. So in a situation like that, first step is treating the whole system as one whole object. So in this situation, we have 2 kilograms plus 1 kilogram. We have something like that, 3 kilograms. The applied force is 21 newtons. We also have force of gravity, which is 30 newtons. And we have normal force, which also is 30 newtons. It must cancel force of gravity. And here we also have friction. Well, strictly speaking, we don't know yet what's happening. 21. Is it sufficient to move it, or it's not? Static friction has maximum value. The force of static friction can have any value from 0 to the maximum. The maximum value of the force of static friction is supposed to be equal to the coefficient of static friction, which is 0.5, times the normal force, which is 30. So that gives us 15 newtons. So if the applied force was 15 or below, nothing would be happening at all. It wouldn't be not enough to make it moving. And the force of friction, the actual value of the force of friction, would be equal to the magnitude of the force we are applying. If we're applying 14, friction is 14. If we're applying 1, friction is 1. But if we're applying 16, 17, or 21, that's it. it's moving, and there's a force of kinetic friction now opposing this motion. So to calculate the force of kinetic friction, we have to use the same equation, but a different coefficient. 12. So, well, turns out that the net force equals, well, let's write it down. 3 times acceleration equals 21 minus 12 equals, I meant 9 newtons. 9 over 3, 3 meters per second squared. Now if I want to calculate the force acting actually, let's keep it 3 meters per second squared. So this top block is moving with the same acceleration, 3 meters per second squared. The mass of this block is 1 kilogram. So the force, the net force acting on it is equal to 1 times 3 equals 3 newtons. What force is that? Well, it has 3 forces acting on it. Gravity, normal, which cancel each other out. And here, there is a force of static friction, which is acting on it. And you see, 3 is less than 15. So the maximum value, if we read the problem, the coefficient of static friction is the same for both surfaces in contact. So the maximum value the friction can provide here is also 15 newtons. That's why if we start pulling stronger and stronger, eventually this force reaching 15, and if we move it stronger, it actually starts sliding off because friction can't prevent it from sliding off anymore. Well, but that's a different situation. This answers the question. That's it. Of course, for this box, for this one, we also have, well, 21, 12, and here we should have 3, and here we should have that friction. No? Where is it? That's not, well, sorry. That's not 12. That's not 12. If I draw a free body diagram for this box only, this friction is supposed to be equal to the coefficient of kinetic friction times this mass, which is 2, times gravity, which is 10. So 0.4 times 2 times 10, 8. Here, I made a mistake. I forgot to include the force acting from the top box on the bottom box. So my calculation of the force of friction is wrong. The correction is in the next lecture. All right. So, yes. Why do we have 3 arrows? There's only 2. It's just when we deal with that box only, yeah, that's what should it be. But come on, you see, 8 and 3 gives 11. So if we treat it as one whole system, it again gives the same kinetic friction we've got before for the whole system. All right. Is it possible to change the origin? Yes, it is, but I wouldn't do that. Why? We choose the origin, we choose the direction. So, but I would stick to my choice until the very end of the solution, until the problem is solved. Otherwise, we might confuse ourselves. If we choose the origin, we choose the positions. It doesn't affect velocity, acceleration, force, or displacement. But the actual position might be different, and why think about it? Keep setting, yes. So keep, stick to your choices. The only thing, there is no such thing as initial distance. There is initial position, there is final position, and there is distance traveled. Crossing the river. Well, we have to know the difference between two situations. This is situation number one, this is the situation number two. The situation number one, that's supposed to be your actual distance traveled, as short as possible. So that's supposed to be the velocity relative to the ground. Situation number two, you don't care about shortest path. You're aiming perpendicularly, but the stream moves you down. So this will be your actual displacement. Your velocity relative to the ground will point like this. And at this point, we just have to remember that this situation also gives us the fastest way to cross the river. That's it. Shortest path, fastest way. If you want to calculate the time, again, you can do it differently. You can calculate the total distance traveled. That's this hypotenuse. And then you could use the speed relative to the ground. Or you can use only horizontal component of this, yeah, which is the width of the river. But in that case, you should use the velocity of the boat relative to the river. No, 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 no. That's it. No. Actually, that was the last question, so actually I can spend some extra time on that. Okay. Case 1, case 2. This is how you aim it. This is, let's say, the velocity of the stream, and that's going to be the velocity of the boat relative to the ground. This is how you travel. Oops. Can I undo it? It undoes everything, not just the last step. Okay. That's how we aim. That's velocity of the boat relative to the river. Okay. That's the velocity of the stream, water relative to ground. So this gives us the velocity of the boat relative to the ground. And so again, this is where you end up eventually. That's your total displacement, delta R, delta R. Now, here, the case number 2. First of all, you can imagine that you aim straight up the stream and see what's happening. And in general, conclusion that it doesn't matter at what certain angle do you aim above the equation should be all the same for all answers. So if for this answer, for this direction, the answer is working, it should work for all other. But you also can choose a certain angle, 45, for example. And the thing is that the length of that arrow must be exactly equal to the length of this arrow. So 1, 2, 3, 4, 5, 6, 7, 8. Otherwise, it wouldn't work. 1, 2, 3, 4, 5, 6, 7, 8. That must be exactly the same. So in this situation, now the blue arrow also has to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that would give you this. So you would be traveling like that. And now what you want to do is just to probably the easiest way, choose one simple case like 1, 1. So it's going to be here 1, 1. That's, let's say, 10, 10, and just calculate it. Just compare. Do it once. Do you know how to do that? Yeah. So that's my general advice to any situation. When you're not sure how it might work in general, choose convenient numbers, convenient, and work them out. What works for a specific case should give you the answer normally to a general case as well. So here, yeah, it's very easy to solve now because you have 45, 45, 45, 45. Okay. Any questions? Yes. Stream. They all have the same meaning. The black arrow represents the velocity of the boat relative to water. The blue arrow represents the velocity of the water relative to the ground. The red arrow represents resulting velocity of the boat relative to the ground. And the long black arrow represents the total displacement. Questions, please? So please press 1. That's an A. I'm going to start a new topic. So you're leaving and you're missing some new topic stuff. Time is what? Of course, we can't waste time. So if you don't have any questions, and that's what you're telling me right now, all I have to do now is just moving on and keep going. Talk. Yes?
Would you be able to do a tension question?
What do you mean?
Just like if we have two masses and then calculate the two different tensions.
What did you press?
I pressed 1 just.
So you contradict yourself, right? If I remember, it was something like this. It actually was in the elevator. So let's do one specific example. Let's make it move with acceleration pointing up and acceleration equals 2 meters per second squared, like in my example with 2 boxes in the elevator. So again, the general strategy is the same. I don't know, 1 kilogram, 3 kilograms. Does it look like a K? No. Oh. I gave up. So first what we can do is to treat it as one system composed of 2 objects with a total mass of 4 kilograms. So for this system, there is tension number 1 and force of gravity acting on the whole system. That's it. This, what we call the internal force of that system, it's inside. The internal force cannot change the acceleration of a system because it's not a part of the Newton's second law. The Newton's second law includes only external forces, forces acting from the outside on the system. So that's why here we only have tension and gravity. So for the positive y direction, m times a equals tension minus gravity. So 4 times 2 equals tension minus 4 times 10. Tension equals 40 plus 8, 48. Yes? It depends on your choice of the system. This is how I made my choice. And just in a second, I want to make a different choice, and that force will not be internal anymore. If I choose my new system like this, the top ball only, now what we have here is same T1, because it's the same string acting on the same ball. But in addition, we also have tension T2, and of course we have gravity mg. But that's going to be a different gravity now, the gravity acting on a 1 kilogram ball. But still, that 1 kilogram ball travels upward with the acceleration. Well, I don't know actually how does it travel. I have to read the problem. But we know that the acceleration points up. That's it. That's sufficient. So for this ball, 1 kilogram times 2 has to be equal to same tension, number 1, 48 T1, minus mg, which is 1 times 10, minus T2. For this system, the same force now is not internal, it's an external force, so it has to be a part of the second law. And we can use it to calculate this tension number 2. Right? T2 will be equal to 48 minus 10 minus 2. 36. Well, we can check our calculation. Hopefully it works, because we always have the third choice of a system. We can look at the bottom ball only. And in that situation, the free body diagram should look like this: T2 mg, second m. So hence, this mass, which is 3, times this acceleration, which is 2, should be equal to T2 minus this mass, which is 3, times acceleration due to gravity, which is 10. So T2, again, is indeed equal to 36 newtons. Matches. Everything fits. So the internal, the external, it's not written in skies, in blood. It depends on our choice. Thank you. So, but on Wednesday we have a regular lecture, energy. Yes?
Oh, I was just wondering, are you gonna put this on the platform?
Yes.
This picture? Okay, cool.
I'm gonna, yeah, of course, all the slides.
So the question about 26.
Yes, excuse me. I'm listening.
Okay, so for the box, which is the smallest,
Yes.
if you only look at this block, since
Only top block. So, how many forces are acting on it?
I know that the force should be towards the right, but
Which force?
uh,
Force of gravity points down.
yes, force of gravity.
Normal
points
force
down.
points up.
Yep.
So when you say this has to be force pointing to the right, what is the nature of that force?
Nature. Is it the force of the block 1 to the block 2?
Absolutely. And what is the nature of that force? How do we call it? If two blocks are in the contact, we call it the contact force, and that force has two components, and each component also has a name. One name is normal. What is the second name for another force?
I don't know.
Frictional?
Frictional?
Yes, force of friction. Frictional force.
Oh, okay. But so then the normal force would point to the right, and then the friction.
Normal force points up because it's always perpendicular to the surface. The surface is horizontal, so normal force is vertical.
But since the friction force should point towards left, I guess.
Nope.
Why? Wait,
How does acceleration point?
the acceleration of block 2
Yeah,
point towards the, I don't know, to its right?
to the right, exactly. So
So
it must be a force which provides that acceleration. If there is no force pointing to the right, the acceleration can't point to the right. If acceleration points to the right, it must be a force pointing to the right.
So are you
It
saying
has to be a force directed to the right. Otherwise, the acceleration could not be directed to the right. What you said?
so are you saying that the only force accelerating the mg and the mv is the friction force towards right? That's what causes the acceleration.
Exactly. But that only for the box on the top.
Yep.
For the box, for the bottom box. The acceleration because we pull the string.
So the friction would be between the block and the table, right? So towards left, to the left.
Well, for this box, you have two frictions, here and there.
Both to the left.
No. Uh, yes, actually, yes. Both,
Okay.
both to the left.
Okay.
You're
I
right.
see. Okay. But if we force a large enough force onto the to the block 1, which makes the block 1 moves, but the block 2 may stay the same. So how would that be?
Against the motion. If the block starts sliding off in that direction, frictions acting from here on here still should point to the right. It will not be static friction anymore. It will be kinetic friction.
Oh, I see. So the graph for the forces onto the on the block 2 would not change, basically.
Diagram would be the same.
I'm sorry, I'm still not sure about this. The time and location of the time and location of the